G'day chemistry students. In this video, we're looking at dot points 6.2.2 and 5. In particular, we're focusing on what pH is, how it's defined, how to look at using it in calculations. Let's get into it. So first off, pH is an index of hydrogen ion concentration. In previous videos, though, we've talked about the idea that hydrogen ions are able to turn into hydronium ions. So we can consider that these two concentrations are effectively interchangeable. So you're going to hear me talk a lot about hydronium ion concentration and hydrogen ion concentration, depending on the context, but realistically, they mean the same thing, certainly when we're talking about pH levels. So pH is an index of how much hydronium or hydrogen ions are present in a solution. What we can see here is that as the pH increases, the amount of hydronium or hydrogen decreases. And depending on how much of those substances are present, we can define our substance as either acidic, neutral, or alkaline. What we should be able to see, though, is that as we increase our pH by 1, that this is not reflected in the hydronium ion concentration. We don't go up by 1 and then up by 1 in concentration of moles per liter. In fact, or not up but down, I should say rather. In fact, what we see is that there is a reduction by a factor of 10 every time we increase our pH by 1. So if I go up by a pH of 1, I divide the hydronium ion concentration by 10. And that pattern exists the entire time. This is a logarithmic scale. For those who are a little bit more math inclined, you may have seen a log scale before. Essentially, we have a relationship where one variable changes by 1 and the other variable increases or decreases by a factor of 10. Now, this is a negative log, which means that the log may not look like what you would usually, see for a regular log. Its shape is sort of inverted, but it is a log scale nonetheless. And we see that in the equation for pH, that pH is equal to negative, and negative is why the shape might look a little bit funny, but negative log base 10 of the concentration of hydronium or hydrogen. It says hydrogen in formula sheet, but as we said before, they are interchangeable. So because it's log base 10, what we see is that a change of 1 in the pH means that we are dividing by a factor of 10. We can use this calculation if we know what the hydrogen ion concentration is. We can use that to determine pH. All we've got to do is put into our calculator negative log 10 of whatever that concentration is. However, if we want to solve for pH here, we're going to need to rearrange our equation and make the hydrogen ion concentration the subject. Now, that requires a little bit of algebra involving manipulations of equations with logarithms in them. This is not something that's really expected of the course. If you want to learn how to do it or do a little bit of revision if you've done it before, I've got a link to a video that you can just sort of look over. Really, the only time that we need to rearrange a log equation is between these style of equations here and the equation at the bottom, making our hydrogen ion concentration the subject. So the formula that we can use is hydrogen ion concentration is equal to 10 to the negative pH. If you use that equation, you'll be able to rearrange that original equation and calculate for the unknown concentration. The last thing that we need to consider when using pH and trying to do calculations is that we can have mono, di, and triprotic acids. What that means is, and we've already seen this in some of our formulas, is that some substances are able to donate more than one hydrogen ion. And if they're capable of donating more than one hydrogen ion, then that needs to be taken into account when we are doing a pH calculation. So for example, if hydrochloric acid is monoprotic, then that means for every one HCl unit that we have, we'll end up releasing one hydrogen into solution. So in other words, whatever the concentration of the hydrochloric acid is, will be the concentration of the hydrogen ion. But that's not going to be the case for sulfuric acid. It's diprotic, H2 here, meaning that for every unit that we've got, 2 hydrogen ions are going to be put into solution. We can see that here, which means that the stoichiometry here is no longer equal and balanced. And what that's going to mean is if we know the concentration of, say, the sulfuric acid, we'd have to double that to figure out what the concentration of the hydrogen ions are. And so when we're doing a bunch of different acid-base calculations, that is going to be something that we need to consider every time. How many protons are present so that we can actually process that calculation. Let's get into a couple of quick calculations to show you what that looks like. So in this first question, we're being asked to calculate the pH of two solutions, 0.1 molar hydrochloric acid and 0.1 molar sulfuric acid. Now the first thing that we need to do is identify our pH equation. So that's pH is equal to negative log 10 of the concentration of hydrogen ions. So we have been given a concentration here, but it's not exactly the concentration of the hydrogen ions, but rather the acid in solution. So when we do our calculations for both of these acids, we're going to have to ensure that we get that concentration right for the concentration of the hydrogen. So when we're looking at hydrochloric acid, we should be able to identify that that is monoprotic, which means that the concentration of hydrochloric acid should be equal to the concentration of our hydrogen ions which are being released. And that makes sense because for every one hydrogen chloride particle that we have, there is one hydrogen ion that can be released. That's then supported by a completed reaction equation, which shows us that one hydronium forms for every HCl unit. Everything is in a 1-to-1 ratio. So what that means is that the concentration of hydrogen ions is equal to 0.1 molar. What we can do next is then substitute into our pH equation. So pH is equal to negative log 10 of 0.1. Chuck that into our calculator. And our pH is equal to 1. However, over on the other side, when we're looking at our sulfuric acid here, we might see that this calculation comes out a little bit differently. Now, sulfuric acid has sulfate as its anion, and sulfate has a charge of -2, meaning that we need 2 hydrogens for every sulfate, H2SO4. Now this is diprotic, which is going to imply that the concentration of sulfuric acid is not the same as the concentration of hydrogen ions when we put it into our water. So if I write out my equation, H2O turns into, just put a plus there as well for our hydronium, H3O plus, and our sulfate, what we should see is that our equation is currently unbalanced. What we will need to do is increase the number of waters and hydroniums from 1 to 2. And what that means is that for the sulfuric acid, there are 2 hydrogens which can be donated onto 2 waters for every sulfuric acid unit that we have. And that's going to have an impact on the resultant concentration. So the concentration of sulfuric acid is not going to be the same as the concentration of our hydrogen ions. In fact, what we will see is we're going to have to double the concentration of our sulfuric acid to match the amount of hydrogen that is being produced, meaning that the concentration of our hydrogen ions is actually equal to 0.2. We can then put this concentration into our pH equation, and that yields an answer of 0.7, and that's correct to 1 decimal place. So moving on to our second question, it's slightly more complex than the first. We're being asked to calculate the concentration of 2 solutions, a solution of nitric acid and sulfuric acid, and we know that they both have the same pH, which is 2.4. So the first thing that we can do is write down the equation that we're going to use. So concentration of hydrogen ions is equal to 10 to the power of negative pH. Because the pH is 2.4 for both solutions, that's going to be 10 to the negative 2.4. However, the problem becomes a little bit more complex when we look at the formulas of both of the acids. We're going to start with nitric acid first. HNO3 is its formula. This means that the substance is monoprotic. Because it's monoprotic, we can make the assumption that the hydrogen ion concentration, which we've just written an equation for, is going to be exactly the same as the concentration of the nitric acid in solution. So that's going to be 10 to the power of negative 2.4. Putting that into our calculator, we should find that that is 4.0 times 10 to the negative 3 moles per liter. However, for sulfuric acid, its formula is H2SO4. It's diprotic. Because it's diprotic, we can't make the same assumption about the hydrogen ion concentration and the concentration of the sulfuric acid in solution. The equation is going to look like this. The concentration of hydrogen ions is going to be double the concentration of our sulfuric acid. So our equation ends up looking like this. Now, as a result, concentration of sulfuric acid in solution, which is what we're being asked to find in the question. Oh, not written that right. Is going to be equal to hydrogen ion concentration divided by 2 if we rearrange. So that's going to be 4.0 times 10 to the negative 3. Keep in mind I've carried that number in my calculator to make sure that I get proper rounding at the end. I'm going to divide that number by 2. So when I divide on my calculator, I get still something that rounds up to 2.0. That's going to be times 10 to the negative 3 moles per liter. So yeah, different concentrations because our two substances donate a different number of hydrogens per molecule. Thank you very much, everyone. In the next video, we're going to be doing some basic calculations involving pH. We're going to be also introducing this concept of pOH. So very similar to pH, but we're looking at hydroxide ion concentration. But until then, have a good one.